Today, we are going to answer one of the most awe-inspiring questions in astrophysics. What exactly happens when two black holes collide? This is not just a simple crash. It is a cataclysm that reshapes space-time, releases more energy than all the stars in the observable universe combined, and sends ripples through the cosmos that we can finally detect here on Earth. Let us begin our journey into the most violent and fascinating event in the known universe. First, we need to understand what black holes are and how two of them end up in the binary system. A black hole forms when a massive star, at least 20 times the mass of our Sun, runs out of nuclear fuel and collapses under its own weight. The core shrinks down to an infinitely dense point, called a singularity, surrounded by an invisible boundary known as the event horizon, the point of no return. Most black holes we know of are stellar mass black holes, with masses between 5 and 100 times that of the Sun. But how do two of these end up orbiting each other? There are two main ways. The first is that they form from a binary star system, two massive stars, born together, orbiting one another, and each eventually collapses into a black hole. The second is that two lone black holes drift close enough in a dense star cluster, like the core of a globular cluster, and get trapped by each other's gravity. Once they form a binary system, their fate is sealed. They will spiral inward and collide, no matter how long it takes. The collision happens in three distinct dramatic stages: the inspiral, the merger, and the ringdown. Let us start with the first and longest stage, the inspiral. For millions of years, the two black holes orbit each other at a relatively safe distance, moving in slow, wide circles. At this stage, they release tiny ripples in spacetime, called gravitational waves. Albert Einstein first predicted these waves in 1916 as part of his general theory of relativity, describing gravity as the curvature of spacetime caused by mass and energy. When massive objects accelerate, they create these ripples that spread outward at the speed of light, stretching and squeezing everything in their path. But when the black holes are far apart, these gravitational waves are extremely weak, carrying away only a small amount of energy from the binary system. This energy loss causes their orbits to shrink very gradually, so slowly that for millions of years the change is almost unnoticeable. As the black holes draw closer, the pace quickens. When they are about a few hundred kilometers apart, the gravitational waves become far more powerful, carrying away energy at a staggering rate. The orbital speed skyrockets from a few thousand kilometers per second to nearly half the speed of light. The black holes spin faster and faster, their event horizons almost touching, swirling around each other in a death spiral. This phase creates a unique signal called a chirp in the gravitational waves. The frequency and amplitude of the waves rise rapidly as the black holes spiral inward. Imagine the sound of a whistle being blown faster and higher pitched, that is, the cosmic chirp of a merging black hole pair. By the final moments of the inspiral, the two black holes are moving so fast that they complete thousands of orbits every single second, and space-time around them is twisted into a chaotic, turbulent mess. This is the calm before the most violent storm in the cosmos. The second stage is the merger itself, and it is over in a fraction of a second less time than it takes to blink your eye. This is where the two black holes smash together and fuse into a single, more massive black hole. The moment they merge, the gravitational wave emission reaches its absolute peak, releasing an amount of energy that defies comprehension. Let us put this into perspective. The merger of 230 solar mass black holes releases more energy in 0.2 seconds than all the stars in the observable universe release in total over the same period. That is, 50 times more energy than every star, every galaxy, every quasar, and every supernova combined. This energy is not released as light or heat or radiation we can see. It is all locked into gravitational waves, ripples, that tear through spacetime at the speed of light, warping reality itself as they travel. The merger is so extreme that even the laws of physics are pushed to their absolute limits. The event horizons of the two black holes merge into one, and the singularity at the heart of each is now a single, infinitely dense point. The newly formed black hole is not a perfect sphere, though it is wildly distorted, lopsided, and unstable, like a bell that has just been struck with a cosmic hammer. This leads us to the third and final stage, the ringdown. Just like a bell, vibrates and fades after being hit, the distorted new black hole rings as it settles into a stable, spherical shape. During this phase, the black hole emits additional gravitational waves, which rapidly decrease in amplitude as the distortions smooth out. These oscillations are called quasi-normal modes, and they fade away completely within a few milliseconds. Once the ringdown ends, we are left with a single, quiet, massive black hole, larger than the two original ones combined, but not quite the sum of their masses. A small fraction of the total mass, around 5% to 10%, is converted into pure energy and carried away by the gravitational waves during the merger and ringdown. This is Einstein, SE equals mc squared, in its most dramatic form, mass turned into energy on a cosmic scale. For a century after Einstein predicted gravitational waves, scientists had no way to detect them. These ripples are incredibly tiny. By the time they reach Earth, they stretch and squeeze objects by less than the diameter of a proton. But that changed on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. LIGO is a pair of giant detectors, one in Louisiana and one in Washington state, each with two 4-kilometer-long arms at right angles. Lasers bounce back and forth between mirrors at the ends of the arms, and any tiny change in the length of the arms signals a passing gravitational wave. On that day, both detectors picked up a clear, unmistakable signal, GW 150914, the first direct detection of gravitational waves from a pair of merging black holes. The signal came from two black holes, each about 30 times the mass of the Sun, merging 1.3 billion light-years away. This discovery not only confirmed Einstein's greatest prediction, but also opened a brand new window into the universe, gravitational wave astronomy. Before LIGO, we could only observe the universe with light radio waves visible, light X-rays and gamma rays. Now, we can listen to the cosmos, hearing the echoes of the most extreme events in existence. Black hole collisions are not just rare spectacular events, they shape the evolution of the universe. Stellar, mass black hole mergers are common throughout the cosmos, and LIGO has detected dozens of these events since 2015. But even more mind-blowing are mergers of supermassive black holes, which sit at the centers of nearly every galaxy, including our Milky Way. These black holes have masses millions or even billions of times that of the Sun. When two galaxies collide and merge, their central supermassive black holes sink toward the center of the new galaxy and form a binary system, eventually merging, just like stellar mass black holes. These mergers are far more powerful, sending gravitational waves across the entire universe, and they can even kick the new supermassive black hole out of the galaxy center at millions of kilometers per hour, a phenomenon called a recoil kick. Studying these mergers helps us understand how galaxies grow, how supermassive black holes form, and how the large-scale structure of the universe came to be. What would it be like to witness a black hole collision up close? If you were close enough to see it, you would not see the black holes themselves. They are invisible, but you would see the space-time around them warp dramatically. Stars behind the black holes would be distorted into strange, curved shapes, an effect called gravitational lensing. The gravitational pull would be so intense that it would tear apart any planet, star, or spacecraft nearby, spaghettifying matter into thin streams of particles before swallowing it whole. You would not hear anything because space is a vacuum, but if you could convert the gravitational waves into sound, you would hear a short, high-pitched chirp, the cosmic sound of two black holes becoming one. Black hole collisions also challenge and refine our understanding of gravity. General relativity works perfectly for describing these events, but scientists are still looking for clues to a more complete theory of quantum gravity, which would unify general relativity with quantum mechanics. Every merger we detect gives us new data to test these theories, pushing the boundaries of human knowledge further than ever before. These events are laboratories for physics that we could never recreate on Earth, where the most extreme conditions imaginable play out in real time. As we look to the future, new detectors will help us discover even more black hole mergers. The Virgo detector in Europe, Kagra in Japan, and future space-based detectors like LISA will let us observe mergers that are farther away, more massive, and older than ever before. We will be able to map the history of black hole mergers across cosmic time, learning how these events shaped the universe from the earliest moments after the Big Bang to the present day. Every time we detect a new merger, we are not just observing a cosmic disaster, we are unlocking the secrets of space-time gravity and the fundamental laws that govern everything we know. The universe is full of mysteries, but few are as captivating and terrifying as black hole collisions. These events are the ultimate display of cosmic power, a reminder of the immense forces that shape our universe. They connect Einstein's century-old theories to cutting-edge observations, bridge the gap between small stellar black holes and the supermassive giants at galaxy hearts, and give us a new way to explore the darkest corners of space. The next time you look up at the night sky, remember, somewhere out there, two black holes are dancing toward their inevitable collision, sending ripples through spacetime that may one day be detected by our instruments, teaching us something new about the wonders of the cosmos. Please like, comment, share, and subscribe to the channel.